Hello everyone, I'm going to be discussing problem 2 from test 2, which was a doozy for a lot of students, including myself. And this is the infamous loop problem. We have a square loop and we can't use an approximation. So let's go ahead and jump right into it. Oh, sliding off. See, we start off with a square loop in the XY plane with a current of I going in this direction. And we have the square loop is composed of 4 segments all with length L. So to go ahead and approximate, or not approximate rather, but to calculate the electric or the magnetic field contributed by the loop in general, we're going to start by dividing the loop into 4 segments and calculating the magnetic field of each segment as if it were a wire. So we'll start off with the wire equation for the magnetic field contributed by a wire, which I have written out already. Here it is. And for a segment, we first have to calculate R, which essentially was my main issue when I was solving the problem. So I drew a diagram over here. Since by utilizing the right-hand rule, if you were to curl your fingers around the loop in the direction of the current, it would curl in the positive Z direction, so that's going to be the direction of the magnetic field. The X and Y components of the magnetic field will cancel out, so there should only be a positive Z direction magnetic field. The R vector coming from one segment to the Z axis is comprised of a length of L over 2 to the center of the ring, and then a length of D to the distance that we're observing the magnetic field from. And by utilizing the Pythagorean theorem, we can calculate our R value. We've got R squared equals D squared plus L squared over 4, which is the same as A squared plus B squared equals C squared. We go ahead and take the square root of this value here and plug it into our equation as our R value. And just to remind you that this is the equation for the a individual segment of the loop, which is equivalent to the equation of the magnetic field contributed by a wire. After solving all this complicated math, well, not really complicated, but just simplifying it, we're left with the equation for a segment being mu naught over 4 pi times the length of a wire times the current of the wire over the square root of D squared plus L squared over 4 times the square root of D squared plus L squared over 2. Now we have, this is a part of the segment, but as you can see here, the segment, we only care about the magnetic field contributed in exactly the Z direction. So what we have to do is find the component that, only the Z component of this magnetic field. So we do that by using cosine theta of the magnetic field contributed by the one segment. And to find cosine theta, we have to use some geometry. So this is the angle created by the distance D and the R vector. And according to the, I think it's called the vertical angle rule, I'm not sure exactly, the angle vertical to it is the same. The B segment is perpendicular to the R vector drawn, so based on these relationships we can come to the conclusion that theta is equal to 90 degrees minus phi. And as you all know, if cosine is only 90 degrees more than sine, if you were to look at a sine graph or a cosine graph, they're essentially the same, except for one is shifted over to the right or left by pi over 2, or which is equivalent to 90 degrees. So the B segment, getting caught up in my words, the Z component contributed by the B segment, cosine theta is equivalent to the B segment times sine of phi. So as you well know, sine is opposite over hypotenuse. So the opposite would be L over, the opposite to the angle phi would be L over 2. and the hypotenuse is our r vector, which we already calculated earlier. So if you just plug and chug, you're left with L over 2. Sine phi is equal to L over 2 over the square root of d squared plus L squared divided by 4. Now the BZ components is equal to what we had originally calculated for the magnetic field contributed by a segment times sine of phi, which we had calculated here. And we are left with all this complicated math. Not really. I'm not going to thoroughly explain everything that's going on in this equation because I've kind of already talked about it earlier in the beginner steps of the problem. Now this is only the magnetic field contributed by one segment, so to get the magnetic field contributed by the entirety of the loop, we have to multiply that by 4 because there are 4 segments. And after plugging and chugging, you're left with this simple mu naught over 4 pi times 2I L squared over d squared plus L squared over 4 times the square root of d squared plus L squared over 2. And this is, of course, in the positive z hat direction. Now let's move on to part B, which is actually quite simple once you get the base. Once you've solved the first part of the problem, is showing that essentially the magnetic field contributed to the loop at distances that are much greater than the length of the loop itself would is essentially equivalent to the magnetic field contributed by a dipole.